Robots with legs offer some of the most extreme challenges in all of robotics. The physics of dynamic walking, whether with 2, 4, or 6 legs, is a balancing act similar to an inverted pendulum and just as unstable. Even more extreme is the physics of running, which we can compare to a pogo stick, where balancing is interspersed with short periods of flight. Military pack horse robots like Big Dog and the LS-3 already confront the challenges of dynamic stability, and those challenges become even greater in some of the largest, fastest, and smallest of all legged or limbed robots, which makes them some of the most extreme robots of all. The Guinness Book of World Records certified a dinosaur-sized machine called Tridino as the world's largest four-legged walking robot. Tridino was designed and built by a German company, Zollner Electronic. Tridino weighs in at 22,000 pounds, close to the mass of a tractor truck. It's about 50 feet long if you include its tail, and has a diesel engine producing about 140 horsepower. Tridino's top speed is officially listed at 1.8 kilometers per hour, or about 1.1 miles per hour. Now, no worries here, right? You and I walk at about 3 miles per hour, so we are not going to be chased down by Tridino in the next version of Jurassic Park movie. But to be fair, Tridino was not built to be fast. It was built to be large, extremely large. Among legged robots, a speed demon is Outrunner, which runs 20 miles an hour and faster. It's built by Robotics Unlimited. It's about 2 feet tall and weighs in at about 3 pounds. Remote controlled, it has 6 legs that spin around a motor-driven axis. As each leg hits the ground, it flexes under the load just like our legs do. Flexing of a structure is a property called compliance, and it allows the legs to act like elastic springs to store and then release energy. Even faster is Cheetah, a 4-legged robot created by Boston Dynamics. Cheetah, weighing in at about 70 pounds, ran on a treadmill at speeds of up to 29 miles per hour. But unlike Outrunner, Cheetah needed to be tethered and run under controlled conditions to keep it from crashing. In addition, the hydraulic pump powering the robot was off-board, leading some to say that this version of the Cheetah was cheating a little. A version carrying its own power was developed to run outside, and that version is called Wildcat, and it could attain speeds of 16 miles per hour. Now, notice that these fast robots are small compared to Tridino, and with good reason. Physics. The laws of physics create a trade-off between size and speed. Now, the study of size and how it matters is called scaling, and the most fundamental scaling law is purely geometric. It's the surface area to volume ratio, and that's also known as the square cube law, and that impacts form and function in biology and engineering. Let me explain. This is a can of tuna. Its shape is known technically as a right circular cylinder. Now, a big can of tuna is also a right circular cylinder. As long as the ratio of the diameter to the height of the can is the same in both, and they are, then we can say that they have the same shape even though they are of different size. So this is an example of isometric scaling, where the prefix iso, which means equal, and metric means measure. Any variation from isometric scaling is called allometric scaling, where the prefix allo means different. So let's think about area to volume ratio of our size-changing tuna fish cans. If we make the height of the can always equal to its radius, then the surface area of a right circular cylinder is the product of 4 pi and the square of the can's radius, radius to the power of 2. The volume of the same can is the product of pi and the cube of the radius, radius to the power of 3. If we double the radius of the can, say from 10 to 20 centimeters, we increase the surface area 4-fold. On the other hand, the volume increases 8-fold. So at a radius of 10 centimeters, the ratio of area to volume was 4. At a radius of 20 centimeters, that same ratio has fallen by half to 2. So as these ratios show, the increase in surface area is not enough to keep up with the increase in volume. So this is a giant warning that the square cube law broadcasts. Isometric enlargement grows volume faster than area. An important sequel of the square cube law is that the mass and weight of an animal or robot usually increases in direct proportion to the volume. Now let's look at how this isometric scaling of the area-volume ratio impacts the movement of animals or robots at extremes of size. At very small sizes and speeds, movement through air and especially water is dominated by the effects of viscosity, a measure of the stickiness of the fluid. And for us to experience this effect, imagine jumping into a swimming pool full of syrup. The dominance of viscosity is why tiny medical micro-robots from about 25 to 60 microns long cannot glide. Because of their shape and their size and spiral shape, they're called artificial bacterial flagella by researchers at the University of Zurich. By placing a small head of nickel on one end of the micro-robots, the researchers can use a fluctuating external magnetic field to propel and steer these micro-robots. They corkscrew their way forward. Moving that way, they may be able to deliver drugs and even genes to targeted cells. At the other end of the scale, for the big and the fast, fluid forces are dominated by the effects of inertia, the tendency for objects to keep moving once in motion. For terrestrial animals and robots, those that don't move in fluid, the first challenge is to be able to hold up their weight, at least while they're standing still. Weight is the force generated by gravitational acceleration acting on our body's mass. Let's think about terrestrial robots supporting their weight. We'll suppose that they are, how about right circular cylinders? These cylinders, let's just pretend, have a height that is twice the size of the radius, as we've been saying, and the small cylinder that we're going to think about here, let's say has a height of 20 centimeters, so a bit bigger than this. You might think about this in terms of size and approximate mass, like a dog. Now let's imagine a larger cylinder that stands 2 meters tall. So you might think of it about the size in terms of mass of a cow. All right, let's assume that the density is the same for these two cylinders. So their mass then is just a function of their volume, which is 1,000 times greater for the larger cow-sized cylinder. So that's a difference of 3 orders of magnitude. Now, instead of metal in a can, let's imagine that these mammalian masses are supported by bone that forms the exterior of the cylinder. So starting with the dog cylinder, let's make the bone have a thickness of 1/100th of the radius, or about 1 millimeter. Now that's pretty thin, but bone is a remarkable material with high strength and compression. If the bone is all that's supporting that 6 kilogram mass and its associated weight, then we calculate the stress in the bone as the weight divided by that bone's cross-sectional area. The bone sustains a stress of about 19.1 megapascals, which it turns out is well below bone's compressive strength of 170 megapascals. Phew! Now, if we keep the bone that same size relative to the radius, and then we run into a problem with our cow cylinder. The compressive stress within the bone is 191 megapascals, above bone's strength limit of 170 megapascals. Our cow cylinder has just collapsed under its own weight. Now, take a look at some real bones here. This is the long bone from a cow sold as a chew toy for dogs. To be fair to the cows, I thought I'd show you a long bone from a dog too. So here's the long bone from a dog. Take a look at the thickness of the bone in each. There are cross sections here. There are extreme differences. You can see in the cow the additional bone that is needed to compensate for the square cube law. But compensating with more bone brings up another problem. Bone is twice the density of muscle and water. And since density is the ratio of mass per volume, if you converted your body to 100% bone, you'd have twice the mass and twice the weight for the same volume. Mass matters for movement. Newton's second law tells us that if you keep the force constant, then if you double the mass, you're going to halve the acceleration. In the case of muscles, the force that they can generate is proportional to the cross-sectional area of those muscles. As animals get bigger, the square cube law tells us that the animal needs to get bigger muscles or they'll need to only be able to accelerate more slowly. In robotics, one way to postpone this trade-off between size and speed is to build walkers with very light skeletons. In a people-powered giant spider walker, you can see a truss design, also called a space frame, that allows for a cadence very close to that of a human walker, about 1 cycle per second. So a totally different way to solve this problem of getting bigger is to build more forceful motors. The challenge is to increase force and power without increasing weight, friction, or resistance. A team led by Dan Granite, a former engineer with NASA, is working to create a new kind of power system for large robots called hydraulic accumulators. Powered by a diesel engine, the hydraulic system is pressurized, and that potential energy can be released quickly to rapidly move joints. As an attraction at monster truck shows, they envision using this hydraulic system to power, ready for this, a 70-foot tall robot called Bug Juggler. It's to be large and strong enough that it can juggle 3 small-sized cars. The bug in its name refers to Volkswagen Beetles, affectionately known as bugs. Isn't that crazy? So the giant Tradino robot that we've already talked about also uses a hydraulic system. It has a turbo diesel engine that pressurizes 20 gallons of hydraulic fluid fed through a series of tubes and into leg actuators. That hydraulic fluid moves the pistons that in turn create the torque that powers the joints of the legs. Now, Tradino is remote controlled. It has literally several thousand parts, including 262 sensors and over 40 different hydraulic motors. So it can't be controlled by a single human. Way too complicated. So what Zollner did was to create functional modules. Each module has its own localized control, mostly autonomous, that is then controlled with an overarching control system into which the human taps. With high-level commands, the human guides the control of head, tail, and legs. Making Tradino walk was a serious challenge. The legs have to support the weight of the robot and move in just the right way, a pattern of footfalls that we call a gait when we are thinking about humans. To build a gait involves careful coordination. The engineers had to carefully examine animals and their movement patterns in order to solve this problem in Tradino. Now, why do 2 of the world's largest limbed robots, Bug Juggler and Tradino, use hydraulic systems? Hydraulic systems are useful because they allow the motor to be centralized. The alternative we tend to see in smaller robots, like Hexy here from Robotics, is to put a motor in each joint that's associated with a limb. Let me get Hexy up and running here and show you what's going on. So I'm going to plug in Hexy's power, and then the USB here to the computer, and I'm going to call up the program Pomoko that Robotics makes available for you to run Hexy. And let's ask Hexy to use its motors, let me get the cord out of the way, to stand up. There we go, very cool. So Hexy is standing up. Now, a great thing about all these individual motors is that you can easily program different behaviors by controlling each motor. So Hexy can stand, as you can see. Now, I'm going to control these motors here, and Hexy's going to point. Sometimes he tips over, so give him a little slack. Pointing, very nice, Hexy, thank you very much. And you know what? We're even going to try Hexy dancing. So now we'll get Hexy moving here. Hexy, dance! All right, we need some music. I'm not sure what the theme music would be here for Hexy dancing. So if you think about Hexy scaling up in size, you can see the problem that's introduced by Newton's laws, right? If we have big motors in each joint, then they have to be accelerated, right, with each step. So here are the servo motors. So here's the servo motor out here that controls this joint. Here's the servo motor right here that controls that one. And the servo that controls this one is there. So the motors are out in the limb. So as Hexy grows, more and more of the motor's torque goes just into accelerating the motor. And eventually a giant-sized Hexy couldn't even move. With hydraulics, You keep the motor or motors inside the body, and you use fluid to transmit the force out to the joints. So for very large robots, a hydraulic system is a clever way around a physical limit. If we look deeper into the design of Bug Juggler, we can see that the plan for juggling cars represents another kind of extreme: largest exoskeleton robot. The Bug Juggler idea is to put a human juggler inside the head of the robot. He's inside there and attached to a haptic sensory feedback interface. Basically, he straps on sleeves and gloves that take the movement of his arms and translates them to the movement of the robot. Now, you sci-fi fans, you may be saying, it's about time. Remember the Jaeger mechs in the movie Pacific Rim? No? Well, how about the Armored Personnel Unit Corps and their mechanized bipedal combat suits in Matrix Revolutions? Or how about amplified mobility platform used by the soldiers at Hell's Gate in Avatar? Robot fighters and robot jocks. Iron Man. These are all powered exoskeletons that increase the capacity of human beings, their strength, speed, size, ability to use and wield weapons. These sci-fi exoskeletons are mobile robots. But Bug Juggler at 70 feet is not. A tall robot tossing cars and rotating limbs has a big problem: balance. It would take additional power to move legs around and to control posture and balance. So if you want a big robot to toss around large objects, the practical first step, so to speak, is to anchor that robot underground using steel I-beams. Do we see the same kind of trade-offs happening at the other end of the scale, at the really small? Well, we see challenges for sure, but of a different kind. You've already seen the tiny capsule robots that you can swallow when we talked about medical robots, Shrinking the Explorers and the Amazing Voyage movie. These capsule robots are not the smallest robots around, however. There are many robots based on the bodies of flies and bees. Robotic flies and bees, tiny microflyers. This clip shows a robo-bee from Kevin Ma's project in Dr. Wood's microrobotics lab at the School of Engineering and Applied Sciences at Harvard University. The quarter is shown for scale, and what's impressive is that the tiny little robot flies at all. To build a micro machine that flies and can be powered and controlled with lateral maneuvers has been a big challenge. For small robots, a major problem is having enough fuel, enough energy, as we've been calling it, on board. As Ma and his colleagues have said, quote, long-duration power autonomy awaits advances in small, high-energy density power sources. In other words, we need better microbatteries. Another problem related to power is that electromagnetic motors, like we've used to power the wheels or flap tails in our robots, don't scale very well to small sizes. The magnetic and electrical fields at very small sizes just don't produce much force. The RoboBee team addressed the tiny motor problem using piezoelectric flight muscles that converted changes in electrical voltage into a change in length of the tiny motor. Unlike muscles, and better frankly, these little strips of bistable ceramic crystals can pull like muscle, but can also push like muscle cannot. A linkage system in the transmission amplifies that small displacement of the piezoelectric strips into the larger motion driving the wings. To minimize the power that it takes to flap those wings, a flapping frequency is used that lies close to the resonance frequency of the whole flight system. Resonance frequency you can think of as the note, the pitch produced when you pluck the string on a guitar. The RoboBee's wings have a resonance frequency too, and it doesn't take much power to keep a guitar string or the bee's wings flapping once you get it plucked and you get it moving. One problem trying to flap the wings near this resonance sweet spot is this: how do you adjust thrust? So you don't want to change the frequency. What Ma and his team did was to design a control scheme where they would instead change the amplitude of the wing beat. Larger wing beat amplitudes create more thrust. So to have a robot turn in flight, they could take advantage of having a separate motor for each wing, changing the amplitude of each wing independently. The RoboBee is something mighty small indeed, with a wingspan of just over an inch, about 3 centimeters, and the robot itself weighs only 80 milligrams. For comparison, a penny weighs in at 2,500 milligrams, nearly 30 times much as the robot. The plan in Dr. Wood's microrobotics lab is to make RoboBee autonomous, both in terms of carrying its own energy supply and in terms of behavior control. They imagine swarms of these RoboBees working as pollinators. To do this, each RoboBee will need to be able to collect and then distribute pollen, hence the tiny appendage that hangs off the bottom of RoboBee. Now you may ask yourself, why build a robot to pollinate plants? Don't we have bees to do that? Well, you may have heard that the honeybees we depend on to pollinate our fruit bushes and trees are in trouble, suffering from what is called colony collapse disorder. RoboBees could serve as stand-ins in situations where live bees are unavailable. Making RoboBees autonomous highlights the trade-offs, by the way, that you encounter when you try to make microrobots. The longer that you want to make your robot to operate on its own without a tether, then the bigger you have to make the battery. And bigger batteries mean bigger robots. One intriguing way around the problem of putting energy and control on board a tiny robot is to build a world outside the robot that contains both. If you can't modify the robot, modify the environment. That's one of the principles of robotics that we've been learning. This approach is allowing nanobots to be created. With nanobots, the idea is to make tiny robots that operate on the level of molecules, the same scale as we saw with the molecular electrical motor. First, let's get ourselves oriented to the size scale we're talking about with nanotechnology. The scale is typically from 100 nanometers down to 1 nanometer, which is 1 billionth of a meter. At this scale is where single molecules, like DNA, live. So when we talk about building nanomachines, we are talking about being able to manipulate single molecules. You've probably worked with molecules yourself before, and the field is called chemistry. But traditional chemistry is manipulating billions or trillions of molecules and not individual ones. So amazingly, a team at Tufts University has built an electric motor from a single molecule. They bind a single molecule of butyl methyl sulfide to a conductive copper surface. Using a scanning tunning electron microscope, they then place an electric charge on that molecule. The charge causes side chains of the sulfide molecule to rotate, and changes in temperature control the rate of rotation. And while these nanoscale motors aren't yet ready to start powering nanorobots, there is work elsewhere on nanoscale walkers. Kyle Lund at Arizona State University and his colleagues built what they call molecular robots, and using DNA is the key. Other researchers had figured out that a molecule of DNA could walk along a track of DNA, built of DNA, if you will. And these are called DNA walkers or nanowalkers. Now, one thing about DNA that you probably remember from biology class is that it prefers to bind with itself and to create double strands. So you can take advantage of this self-attraction and build the track itself out of DNA strands. A random process known as diffusion will swing one of the legs free of the walker and into position to hybridize with the track. That chemical change of the walker signals the trailing leg to release. So what Lund and his team did was to figure out a way to make that walking not random, but directed. So rather than trying to program the DNA with those instructions, they built the track with directionality on it. In other words, they put the information for the control of movement into the environment. And because these directed walkers have 3 deoxyribosome legs carrying another molecule, they're often called molecular spiders. And because they can move autonomously and in a predictable way, Lund calls them molecular robots. And they're just 4 nanometers long. So what's really impressive about the molecular robots is that Lund and his team could build an environment out of what is called DNA origami that contained information for the nanobots to start, follow, turn, and stop. One trade-off that nanobots encounter is that they move slowly. Lund's molecular robots, when they are really moving quickly, can move about 90 nanometers in 30 minutes. That's about 3 nanometers per minute. And remembering that the molecular robots are about 4 nanometers in size, then they move a little less than 1 body length per minute. For a crazy comparison, let's think about how fast Tredino walked. In absolute speed, Tradino moves much faster than our DNA molecule robots. 1.8 kilometers per hour, 30 meters per minute. Now let's think about how the speed converts to body lengths per second, or body lengths per unit time. Tradino is officially listed as having a body length of 15.5 meters. We divide 30 meters per minute by 15.5 meters and we get a relative speed of almost 2 body lengths per minute. By this measure, we have the largest and the smallest robotic walkers moving at about the same relative speed, 1 to 2 body lengths per minute. Very cool. Now, in absolute terms, Outrunner moves at 33 kilometers per hour and Tradino at 1.8. So Outrunner is almost 20 times faster in terms of absolute speed. But the difference is even larger, stated in terms of body lengths. Outrunner stands about 0.6 meters tall, so let's put its speed in terms of that body length. If we take a speed of 33 kilometers per hour, or 33,000 meters per hour, we get 55,000 body lengths per hour. We divide that by 60 minutes to get an amazing 900 body lengths per minute, a speed in terms of body length that is hundreds of times faster than Tradino or our molecular robot. So what's going on here? Why is it that robots at this intermediate size can be built to be the fastest-legged creatures? Well, let's start by looking at how Outrunner works. Outrunner is biologically inspired. The legs are key here, acting like individual pogo sticks in much the same way that your legs work when you are running. And as your leg hits the ground, it compresses, storing energy in internal springs. And that spring energy can be reused to help propel us, or Outrunner, forward and upward, pushing it as the leg rotates backwards. Now, Outrunner is remotely controlled, turning by virtue of shifting its center of mass, like leaning into a turn. And the speed of rotation can also be controlled, and that helps. So Outrunner is very efficient. What that means is per step, per body length, very little energy is used. The battery on board will last for 2 full hours. That's outstanding mission time for something moving so quickly. Another aspect of Outrunner's design that makes it efficient are those spring-like legs which we mentioned, which store and return energy for propulsion. In addition, those legs are lightweight, and they don't have to be accelerated back and forth like our legs do, right? We're doing this. They're rotating around in a circle like a wheel, and so you avoid the inefficiencies of swinging. In robotics, we refer to a wheel-leg hybrid as a WEG, W-H-E-G. So, strictly speaking, Outrunner might not be the fastest legged robot after all, but it's great for seeing how fast legs can go. So let's get to the basic mechanics of legged locomotion. As any sprinter knows, speed is the product of your stride length and your stride frequency. And what limits your speed as you walk or run, in part, is that your stride length is limited by the length of your legs. When you run, one of the nifty things that happens is that you actually launch yourself in the air. You're leaping from one foot to the other. And that aerial suspension actually increases your stride length. Based on stride length alone, we would expect the largest animals, then, to be the fastest. A horse is a great example of a big and very fast animal that takes advantage of its long legs. Secretariat holds the record for the fastest running of the 1.2-mile Kentucky Derby. He did it in just under 2 minutes, so Secretariat clocks in with an average speed of 37 miles per hour. So the trick, if we were to redesign Outrunner to make it faster, would be either to make the legs longer or have the legs spin faster. Would there be any limits? Let's do this thought experiment. We keep the legs spinning at the same frequency, but we make them longer. As their length grows, so does the velocity of the foot, the tip. No problem. But as velocity grows linearly out there at the tip of the foot, kinetic energy grows with the square of velocity. So if you go twice as fast, the kinetic energy of impact, boom, when you hit the ground would be 4 times as great. And what does that mean in practical terms? Lengthen the legs, speed up the feet, and then you'll break them off. They'll start snapping. So what to do? Obvious. Make the legs stronger. Using the same materials you have, you can do that by adding material, making the legs thicker. But that adds mass. That added mass also acts to increase the energy of the impact of the foot with the ground, so you still break legs off. Now, after that mishap, you might start looking for a different kind of material, something like carbon fiber that is stronger without adding more mass. But there's no infinitely strong material, so legs will break if they are long enough or spin fast enough. The team building the Cheetah robot broke dozens of legs on their way to setting a new indoor speed record. So the general take-home message here is that scaling works for animals and robots. You need to scale your skeleton, your support structure, allometrically, not isometrically, to compensate for volume and mass increasing faster than the bone's cross-sectional area, or muscle's ability to generate force, or a motor's ability to generate force. So this is one of the major trade-offs in legged robots. Legs longer need to be stronger. Speed and size are linked to each other by the laws of physics. The ability to generate more force per unit mass is key for the largest limbed robots. To reduce mass as we push the upper limits of size, we can use strong materials and lightweight structural arrangements to overcome problems that come along with simple isometric scaling. The ability to have energy and motors on board are challenges for the smallest robots. You've probably thought a way around this whole problem with legs, by the way, turn them into wheels. Well, wheels have distinct advantage of not impacting feet. They roll over the ground, and this does indeed let us spin wheels quickly. So why bother with legged robots? After all, wheels can spin quickly, carry heavy loads, and are less likely to break. Well, ever try to get a baby carriage or a wheelchair up steps? Ever go hiking over boulders? Legs can be picked and placed, lifted up and over obstacles or steps, and that's very hard to do with wheels. Yes, tracks offer great traction compared to wheels in rough terrain, and on soft ground, tracks can be more stable than legs, but the losses to friction from tracks are considerable. And for truly uneven terrain, legs will continue to offer a couple of tantalizing advantages. Robots with legs have the potential, unlike robots with wheels or tracks, to crawl and climb over obstacles taller than the robot itself. Robots of extreme size or speed pose extreme challenges for robotics, and using legs increases those challenges even more. But for moving through extreme environments, robots with legs will not be the only cool examples of what is possible, but they will be the extreme examples of what is useful.